Hello, everyone. I'm Uendert Andrade, a postdoc at the University of Michigan, and today I will present the latest BO measurements from the 3 years of DESI observation or data release 2. I will walk you through how we obtain and validate our results, ensuring they are robust for cosmology inference. Before diving to the results, I wanted to acknowledge the incredible effort behind DESI, in particular, the sponsor and institution, and of course, a lot of hardworking scientists, including early career scientists. As you may have seen in other DESI talks, what makes DESI exciting is that it allows us to create the largest 3D map of the universe. We have access to multiple tracers covering a range of cosmic time. In particular, we use bright galaxies, luminous red galaxies, and emission line galaxies, quasars, and Lime alpha 4s. So using these traces, we focus on one of the DESI drivers, science drivers, and which is the Baryon acoustic oscillation, or the BAO. These oscillations are imprint of sound waves from the early universe, driven by the interplay between gravity and radiation pressure. Essentially, this means that there is a preferred separation between galaxies, and we are more likely to find galaxies separate by BAO scale compared to other distances. So that the way we use BAO as a cosmic ruler is by connecting the BAO scale with distances, as illustrated here in this diagram on the right. This way, we can track the universe's expansion at different time and probe things like dark energy. So how do we measure the BAO signal in our data? As I mentioned, galaxies prefer to cluster on the BAO scale. So when we look at the galaxy correlation function, we see an axis of clustering on the BAO scale. So this bump, which is clearly seen here in this figure, is the signal we are trying to measure with as much precision as possible. Okay, now I won't go in further details, but we employ a technique like density reconstruction to sharpen the peak and improve our measurements. Okay, I won't keep the suspense too long. So let's take a look at the BO signal we've seen DESI DR2. All right, this plot here show correlation functions for different DESI DR2 tracers. As we can see, the BO feature, the peak, is clearly visible in all cases. And we also show the DR1 measurement in gray. Comparing DR1 and DR2, we see a smaller error bar and higher precision given the increased survey volume in DR2. The figure shows here the pre-reconstruction signal versus the post-reconstruction signal. If you stare at the bottom of the two subplot on the right, you can see the sharpening of the peak after reconstruction. Okay, so we now understand how to extract BO scale from the data, but how do we ensure that what we are measuring is accurate and free from biases? For the rest of my talk, I will be talking about how we answer this question. So essentially, we identify, quantify, and mitigate any potential source of systematic. First, to validate our BO results, as we did, was done in DR1, we blinded the data, and then we devised a long list of tests to pass before the BO measurements were unblinded. The tests compare the BO blinded measurements from our base case with various cases that I listed out on these slides. Since there is there's no too much time to go through all the tests, let's take a look at the data split test as an example, especially since this test is an expensive in DR2. Okay, right, since DESI observed different part of the sky under varying observational conditions, we need to confirm that results remain consistent across different parts. So to do this, we split the data in 3 ways outlined here, and then we run our BO analysis on these 3 data splits and compare results to the baseline. And what we find that no significant deviation from the baseline, as also here indicated by the KS test. This means that our measurement is not impacted by observational systematic. Since we are limited on time, I will show you a summary plot showing the results for all our tests. As a reference, the gray dashed line highlights the regional split tests we just discussed, and we see that across all cases, parameter shifts are small and well within the expected statistical uncertainty. And that it's true even for the most extreme cases. So the bottom line is our BO measurements are robust to a wide range of analysis choices as well as observational systematics. Now let's take a look at, let's talk about the statistical uncertainty in our estimate, the statistical uncertainty in our measurements, right? We, of course, want to ensure that our statistical uncertainty estimates are robust and unbiased. So to do so, we compare BO parameters from our individual mock realizations to the statistical scatter expected from a Gaussian distribution. In this plot I'm showing here, the scatter points represent individual mock realization, while the dashed and dotted contour indicated here the 1 sigma and 2 sigma confident regions. So if our error are underestimated, we would have seen many points outside these contours. On the other hand, if our error are overestimated, most of the points would be tightly clustered in the center. Looking at these results, we see that the points are nicely distributed within the confidence contours here, indicating that our error estimates are well characterized. Okay, based on this, we confirm that our covariance matrix accurately captured the statistical scatter in our measurements. In other words, our uncertainty are neither too conservative or optimistic. Okay, finally, let's look at the systematics. We account for 3 kinds of systematic uncertainty in DR2, and these are theoretical modeling, Halo occupation distribution, HOD, and fiducial cosmology assumptions. The slide includes some more detail in case you are interested in. Now we've talked about validation tests, statistical and systematic uncertainty. Let's look at the final BO result. The figure here shows the correlation function around the BO scale after reconstruction. As discussed earlier, we see a distinct peak around the BO scale, and we detect this with remarkable precision across all tracers with detection significance between 5.6 sigma all the way up to 14.7 sigma. Now that we have measured our BO, we are ready to go to cosmological distances and compare our distance to a cosmological model, for instance. Okay, that's what I'm showing here in this plot is the Hubble diagram. Essentially, it's the BO distance measured across multiple tracers, each capturing the expansion history of the universe at a different redshift. DR2 measurements here are the field points, and the empty ones are the early measurement, the DR1 result. Right away, you can compare the two, and we can see that the error bar has shrunk significantly in DR2, reflecting a 30 to 50% improvement in statistical precision. And finally, let me also briefly talk about the tension we saw in DR1, where there was a 3 sigma tension between our result and those from SDSS. This raised some concern about whether this was due to true systematic or it was a statistical fluctuation, right? With this new DR2 result, we now have better statistics and large survey footprint. And as shown here in the figure, the new DR2 result lies between DR1 and SDSS, suggesting that early discrepancy was likely statistical fluke. So you can find more details on the DESI key paper, but essentially we find that the tension is now like 2.3 and goes all the way down also to 1.5 sigma. As a wrap up, let me highlight some key takeaways. First, DESI DR2 provide the most precise VO measurement to date, right? And the most precise VO measurement, and then the measurements come after an extensive set of tests, and we find that the systematic uncertainty remains subdominant to the statistical errors. And I'm sorry. And this most of what I've presented here is on the validation paper for the BO measurement detailed in our supporting paper Andrade et al. 2025. And for the cosmological result, you can check out the DESI key paper here in these references. So, right. And finally, huge thanks to all people in DESI Collaboration. This work wouldn't have been possible without everyone's incredible effort. And of course, thank you all for listening.